I apologize.
No worries. Thank you, Zvi, and thanks to the organizers for the kind invitation to speak here. So I was asked to talk about post-merger evolution, and I'll be mostly focusing on here on mass ejection and nucleosynthesis, really. And since much has been already discussed at the workshop, I'll try to sort of point out and focus on a few aspects that may not have been discussed at great length yet. So let's get right into it. I hope my slides actually change. Yes, they do. So let me start with this essentially very brief and rough summary, very simplified summary of the merger phenomenology that I'm sure all of you are familiar with. So ignoring essentially those cases that don't lead to mass ejection, namely a prompt collapse in a neutron star merger, or just a neutron star plunging into a black hole in neutron star black hole mergers, we're essentially left with this sort of simplified version of the merger phenomenology, where we get some dynamical ejector early on. Then we have a very complicated post-merger phase in neutron star mergers, lots of problems and still poorly unknown and explored physics, as we discussed here at the workshop. And finally, we'll have a lot of material circularizing around the remnant forming an accretion disk that gives rise to mass outflows on much longer viscous timescales of hundreds of milliseconds to up to seconds. So really, in neutron star mergers, this post-merger phase is much complicated by this sort of early phase of tens to hundreds of milliseconds, where we have a remnant neutron star. So this is essentially the typical situation that we find ourselves in. This is just a typical snapshot from a simulation with Luciano Combi, who is also here on the call, I believe, simulation that we hope to publish soon, later this year. So essentially, we have a very hot remnant that's been shock heated to tens of MeV during the merger. We have some typically high YE, high proton fraction wind material in the polar regions. I'll get into details in a second. And finally, we have some material that starts to circularize around this remnant, starts interacting with this remnant actually. And later on, there will also be some fallback material eventually that will sort of join this concert around the remnant. So in terms of mass ejection, what we have is essentially that this central remnant, the hot remnant, gives rise to copious neutrino emission. It drives a so-called neutrino-driven wind, indicated here in these polar regions. Magnetic fields can also aid here and eject additional material. Well, here we've already heard from Jay about this yesterday, and I'm pretty sure there will be more discussion on this today as well. If that magnetic field tends to be very strong and ordered, so Brian Metzger argued that then essentially this might strongly enhance the mass ejection in concert with the neutrinos. And so we can typically expect something of the order of 10 to minus 4 to maybe 10 to minus 2 solar masses, depending on the remnant lifetime, here assumed to be something around 100 milliseconds or so. Now, something along these lines has been attempted recently. So Carlos has also mentioned this study earlier this morning, where essentially if you take a very strong magnetic field, dipolar field in this case of 10 to 15 Gauss, and put it on a post-merger remnant, you can actually trigger a sort of jet-like structure that also helps to unbind material from the merger environment. And indeed, they find fairly high mass loss rates of 10 to minus 1 solar masses per second initially, which in this case only lasts for a few tens of milliseconds before the remnant collapses, and also reaches fairly interesting speeds up to 0.4 C or so. Now, from Jay, we've heard yesterday that if you wait long enough, then perhaps you can build such a jet-like structure sort of self-consistently, but you'll have to wait for a long time, at least in this configuration. And here also, again, we can see how magnetic fields can can aid in unbinding mass. So here they found something on the order of 10 to minus 2 solar masses in terms of ejector over a fairly long time scale. Now, this whole picture is further complicated by the fact that the remnant undergoes a very complicated evolution, and some of the processes are still poorly understood and explored. This has been brought up at the workshop already. I won't go into much detail. There's interesting merger remnant papers by Wolfgang, also by Shibata, pointing out some potential resistive effects. And so what I find interesting is that essentially this complicated merger evolution, or to be more precise, essentially deformations of the remnant actually interact with the environment. And that's been pointed out also in previous papers by Lehner and Medora et al. They essentially give rise to spiral waves that propagate into the surrounding accretion disk. So you can see a little movie animation of our current simulation, where we now also include magnetic fields. And there's a really interesting competition between essentially MRI-driven accretion onto the central object, but then essentially this opposing phenomenon of the spiral waves that propagate into the ejector and transfer angular momentum into the accretion disk and try to prevent accretion. So that complicates the post-merger scenario, because these spiral waves can also help unbind material and help shape nucleosynthesis properties and kilonova properties. And I believe there's still much to be explored here. So in terms of composition, what actually sets the composition of these outflows, so if we want to understand nucleosynthesis and kilonova signatures, well, chiefly it is essentially determined by electron and positron captures and their inverse reactions. In these polar regions, we have very low density material. As I said, a neutrino and driven wind coupled to magnetic fields will be launched. The equilibrium sort of YE that one can obtain in these winds, expecting these winds, can be sort of broadly understood in terms of an absorption-dominated, non-degenerate regime of material, in which you can sort of analytically derive a expected YE, which for the typical conditions of these post-merger objects lies somewhere in the region of between 0.4 and 0.5. And you can see here how these winds are actually reaching this regime. So color-coded here is YE. Now, in these sort of more polar, in these sort of more equatorial regions, you'll see that the YE has actually attains different values. And so here in this much more dense region of the disk, where essentially electrons are forced into a degenerate regime, at least initially, absorption and emission are both important, and the degeneracy is also very important in setting YE. So the typical equilibrium YE you would expect here is much lower, something around 0.1 or maybe up to 0.2. There's a nice account of the relevant physics in this paper by Bill Borodov. And so if we want to understand the YE of outflows that are launched from this accretion disk or from these sort of more equatorial regions, then things become very complicated, and detailed neutrino transport is important. So the final YE of these outflows really strongly depends on the ejection path of the fluid elements and the timescales as it sort of traverses through different regimes of these weak interactions. So they might originate in a sort of trapped regions where neutrinos are trapped, and both emission and absorption are important. They might then proceed into a stage where mostly YE is then dominated by emission. They might get into lower density and temperature regimes where then absorption becomes very important. And finally, the time scale for weak interactions, given the densities, the low densities will become much longer than the expansion time scales, and so the material will freeze out. And so this essentially then determines the termination point essentially of this YE evolution. You can read this essentially, this sequence, in terms of decreasing density and temperature as a fluid particle, for example, is ejected into space. But you can also one can also understand this in terms of the entire disk evolution as it viscously spreads over time. The disk as itself by itself will undergo these different stages, or may undergo at least several of those. But you can even also understand this as a function of disk radius, because different parts of the disk will actually be typically in different stages. So that's a fairly complicated problem, and for me is a segue to discuss post-merger accretion disks. So why are we actually interested in these post-merger accretion disks? So here's a plot that I hope will be soon published in a review later this year, where I did a simple exercise of trying to use fitting formulae that are now available from numerical relativity simulations that parameterize essentially ejector mass in terms of binary parameters. And so if you sort of integrate over, if you essentially Monte Carlo sample the distribution of galactic double neutron star systems, assuming that this is what we might observe at some point with LIGO as we sample the distribution, and that's still a big if. But if given that assumption, essentially what we find in terms of ejector mass as a function of binary total mass of binary neutron star systems is that largely independent of the exact equation of states or of the exact radius of neutron stars, essentially this disk ejector will dominate over dynamical ejectors. So in this particular example here, 80% versus 20%, for example. And one might then even go one step further and speculate that potentially most of the R process elements or the galactic R process elements might actually be synthesized in accretion disks. A conjecture that is essentially also fueled by other ideas around collapsars, but I will not go into this in this talk. Just pointing out that here I also highlighted the GW17017 system, and so this prediction here is also remarkably consistent with the inferred ejector masses that from the kilonova that we've seen in that event, and also nicely sort of again shows consistency with previous expectations and interpretations that the bulk of this kilonova, the red kilonova, was most likely produced by post-merger accretion disk outflows. So as I said, weak interactions are key in setting the composition and therefore the nucleosynthesis signature and the kilonova signature of such accretion disk outflows. So let's talk a little bit about weak interactions in these disks. So essentially the qualitative picture is that in accretion disk, and for now we'll just imagine a black hole remnant for now, is that MHD turbulence will essentially force material to accrete onto the black hole. It is the source essentially then of heating. And that heating is balanced in some cases by neutrino cooling. So the disk will become dense and hot enough in most cases for neutrinos to be emitted and to cool the accretion flow. You can see a nice dynamo butterfly signature down here. And what drives these outflows is really then a heating cooling imbalance in this what we call hot corona up here, where neutrino emission is severely suppressed because of the low densities as you go off the midplane of the accretion disk. So when do actually weak interactions become important in those disks? Well, you can roughly parameterize this in this quantity that I call R here, which is the ratio of neutrino emission. So the specific heating, if you want, the specific cooling versus the heating, so viscous heating. And when this ratio becomes of order unity, then we expect neutrinos and weak interactions to become dynamically important and also important in terms of setting the YE of the disk and its outflows. Now you can take a simple sort of 1D accretion disk model, and this is work with Jomi D, who's now a postdoc at Los Alamos, and you can essentially ask yourself when this threshold is reached, and this can be sort of formulated in terms of a threshold on an accretion rate, which we call the ignition threshold, that scales with the black hole mass and the effective alpha viscosity of the accretion flow. And so analytically, we would sort of expect something like around 10⁻³ solar masses per second to be a threshold for weak interactions to become important. So you can show that this is for m dot below this threshold, it is essentially equivalent to saying that the weak interaction time scale becomes much longer than the viscous time scale. So effectively, weak interactions are not able to change the composition of the accretion flow. So really, the accretion rate here determines the state of weak interactions in the disk. This can be nicely verified with numerical simulations, which is what we did. So here I've shown a couple of simulations where we sort of devised accretion disks at different initial accretion rates. As you can see here, we measured their neutrino luminosity, the efficiency of radiating neutrinos. And you can see indeed that below this analytically expected ignition threshold, there's essentially very little neutrino emission. While as you go above this threshold, clearly you switch on weak interactions and the disk essentially forgets its initial condition in terms of the composition, at least to some degree. So there's clearly an advection dominated regime of thermal energy and sort of a neutrino cooled regime, where YE is then mostly set by emission, at least over sort of a broad range of accretion of accretion rates. So you can see this here down here in the YE. So essentially below the ignition threshold, YE just stays at its initial value, which here we assume to be 0.1. And as you go above this ignition threshold, you attain a very broad YE distribution. And so that has an important impact on nucleosynthesis, as shown in the panel here on the right. Essentially, as you cross the ignition threshold and attain this broader YE distribution, you also get a nice sort of first to second peak R process elements. And you can also see that depending on what you assume the initial YE to be in the case below the ignition threshold, you can sort of attain fairly high actinide abundances, for example. So it really depends on what the initial conditions are. Those will be suppressed or further suppressed as you go above the ignition threshold. Okay, but this is not the whole story. So as Jonah told us yesterday, absorption is important in outflows, in disk outflows. And so this motivates the following essentially three nucleosynthesis regimes in these disks.
5 minutes, please, Daniel.
Okay, thank you. I'll try to hurry up. Below the ignition threshold, as I said, YE is essentially frozen. We'll get a full R process in an intermediate regime of accretion rates, and then at high accretion rates, we'll get lanthanide suppression. A disk can sort of move through all these accretion disks, through all these, or at least some of these stages over its lifetime of viscous evolution. This is nicely shown here by a recent simulation with Jinyo Lee, a postdoc at Perimeter, where we simulated a very high accretion rate disk, at least initially, of 1 solar mass per second that then viscously evolves through various stages. And you can nicely see how if you look at the outflow in a zoomed out version over thousands of kilometers, you get a fairly high YE material as ejecta from these early phases of high accretion rates. And then as you go toward the interior, things become more neutron rich as you sort of sweep through this intermediate or get into this intermediate regime of accretion rates. Now, in terms of nucleosynthesis, you can also see this nicely. So just focus on the green curve here. So this initial high stage of absorption suppresses lanthanides, and so here in the second to third peak region, you sort of don't get the lanthanide abundances anymore. The lanthanide mass fractions of the solar R process, and especially the actinides, are heavily can be heavily suppressed. But this is sort of rather the upper end of accretion rates that we would expect in neutron star mergers. I get back to this in a second. Just want to make one point that really MHD disks are crucial here. In alpha disks, the outflows are coming much later. They are viscously driven as the disk viscously spreads, and so YE is mostly set essentially by the freeze out of weak interactions relative to whatever the viscous timescale of the disk is. In MHD disks, it's very different. And in the study by Fernandez et al., it was nicely shown how early these DRMHD outflows occur by this heating cooling imbalance on timescales even much shorter than the viscous timescale. And so the YE is here really set by complicated weak physics in these in the early evolution of the accretion disk. Now, the very last point I want to make here is that this is yet not all of the story, most likely, because in conventional neutrino transport, we neglect certain properties of neutrinos. We neglect that they can change flavor. So in principle, doing neutrino radiation transport, one would have to take into account the fact that neutrinos undergo oscillations. As written down here, there are the vacuum oscillations, well known. There's a matter enhancement term, the so-called MSW effect, both of which are not important for neutron star mergers for the purposes of what we're interested in. But it turns out that if you go to very high neutrino densities of 10 to the 30 per cubic centimeter or so, there's a self-interaction term. So neutrinos can forward scatter on themselves and can change flavor. There can be, that is a nonlinear, so the von Neumann equation here becomes nonlinear, and you can have nonlinear phenomena, including runaway modes. So these off-diagonal terms in the occupation number matrix can actually have runaway and build up runaway modes, meaning that neutrinos can very quickly change their flavor. So this may sound a little abstract to you, but it's been a real problem. So it's been discussed in the supernova community for a while, and we've taken this now to neutron star mergers. Here you can see a snapshot from Jinyu's recent simulation, where you see that that actually there are ubiquitous flavor transformations in the outer parts of the accretion disk and in the wind zone, indicated here in this red color. These are nanosecond timescale flavor changes. So they actually occur on faster timescales than the nucleosynthesis and the ejection of the material happens. So they are actually important for setting the composition of the outflows. So these are the first astrophysical simulations where we found a way to actually include this dynamically, at least in an approximate fashion. The bottom line effect is that as neutrinos change flavor, the electron and anti-electron neutrino luminosities are reduced, because those are most copiously produced in all these post-merger systems. And instead, the mu and tau neutrinos will then, the luminosities of those will be enhanced. So essentially you suppress electron, anti-electron neutrino emission. And what happens is that the outflow becomes more neutron rich. So there's a less absorption effect, if you want. And so the outflow material, the disk outflows, become much more neutron rich, as you can see here in the comparison with and without these conversions included. Finally, and this is my last point, showing the nucleosynthesis effect here. Essentially, the difference in this particular example here is between the green and the orange line. The bottom line is that you can enhance the lanthanide mass fraction by at least a factor of 2 or maybe a few. The third peak elements are affected already by an order of magnitude at least, and several orders of magnitude potentially for actinide abundances. So in principle, this could convert something that one would think of as a blue kilonova into actually a red kilonova. It really adds opacity to the outflow. And just to show you that this is not completely crazy and made up accretion disk, here's a comparison between the accretion rates of a recent run by Luciano with SFHO, typical BNS simulation. And I show here also the accretion rate of this particular post-merger accretion disk. And you can see that past the collapse of the remnant, which happens here around 25 milliseconds or so, they actually nicely converge onto each other after, say, 10 milliseconds or so rearrangement phase afterwards. So there's lots to be explored here, I believe, and that adds additional uncertainty into our nucleosynthesis and kilonova predictions. And so since time is up, I just leave you with conclusions here and take any questions you might have. Thank you.
Thank you very much. We have time for one or two very short questions. I'm sorry for running this little bit over time. I'll start with my own question concerning this neutrino oscillations. Were these calculations calibrated with the observations of 87 of the neutrinos in 87A? Because I think that there are quite strong limits on the influence of neutrino oscillations in 87A. And so the question is whether these ideas were compared with the observations.
Yeah, that is a really great question. And I don't have a great answer off the top of my head. So, I mean, we specifically haven't calibrated anything against those particular observations. Cauchy supernovae are a little bit outside of the traditional version of Cauchy supernovae are a bit outside of the range of my expertise. So these are really theoretical calculations. So the first principle-based theoretical calculations where we try to come up with predictions for ejecta composition.
No, I understand, but it's the same physics of neutrino oscillations.
Right.
And my understanding is that there are quite strong limits from that supernova, but we should postpone the further discussion on this to later on. A question by Julian, and then another question by Jonah, and then we'll stop. So Julian, please. Julian? Okay, so let's move to Jonah, and then we'll get to Julian later. Jonah, please.
Thanks for the very nice talk, Daniel. This is very, very cool. On your simulations of, oh, sorry, there's some echo. Can someone mute? On your simulations of the fast flavor conversions, you show this really cool result where you change from where you reduce the electron fraction of the outflow when you turn on these flavor conversions. Have you looked at how the electron fraction appears versus angle? For example, I mean, you might expect a very red kilonova in the equator, but something blue in the polar regions or something like this.
Yeah, that's a great point. So maybe I can just show this plot here again, which I hope you can see, which shows the electron fraction. And so the interesting thing is that there's, as you also mentioned in your talk, there's a clear sort of dependence in angle of YE, and sort of this clearly higher YE material in the poles, and that still translates, at least to some extent, to the cases in which we switch on flavor conversions. And then there's also additionally this radial trend that I pointed out as the accretion disk goes through the various stages of accretion rate and different nucleosynthesis regimes. You also get this sort of radial gradient that essentially imprints the history of the accretion disk evolution. So yeah, there's still an angular dependence here with sort of more neutron-rich material in the equator and sort of less neutron-rich higher YE material at the poles.
But there won't be an angular dependence for different observers because observers, this radiation is not beamed, so observers see the whole both the caps and the equatorial plane. Okay, Julian, last question.
Okay, so try again. And I'm concerned about the status of time dependence in the accretion rate when you start out with, for example, an inflow equilibrium structure. And particularly if you're looking at outer regions where outflows may emerge, I would expect they would be very slow to achieve inflow equilibrium.
I'm not sure I understood the question. There was some echo. So your question is about the initial structure of the disk and how it reaches a quasi-stationary state, and how that affects the outflows.
Okay. Yes, my question is whether, or even how, or more properly, how long it takes to reach inflow equilibrium as a function of radius. Because the initial distribution of surface density need have no particular relation to what you'd expect for example, an inflow equilibrium alpha disk. And there are a couple of timescales here. One is growth of the MRI and the associated stresses. And the second is that although you might have fairly quickly achieve inflow equilibrium in the inner parts of the disk, all the timescales, of course, stretch as you go to larger radius. And particularly at the radii that are the sources of the kilonova ejecta, those timescales can be pretty long.
Yes, I agree. So that's a good point. So maybe I should highlight that in terms of the ejecta. So for the alpha disks, I believe it's true that most of the ejecta will eventually originate from the outer parts of the accretion disk. So as the accretion disk viscously spreads, it sort of lifts out material out of the potential, and so that inflow equilibrium will then be important. In the case of MHD disks, we see that sort of a good fraction, or sort of most of the material. I don't have, unfortunately, numbers for you here right now, but typically what we see is that most of the material is evaporated in the inner parts of the accretion disk, where inflow equilibrium is certainly reached. And so that's really a difference between these alpha disks and MHD disks.
In fact, I'd like to ask a question.
Okay, maybe
clarifying what
Julian,
you mean by that distinction, because if the stresses and the heating are the same, what are you distinguishing?
So
I think that we should stop this. Sorry to stop this discussion. It's very interesting, but I'm told by the organizers that I'm doing a terrible job as a chairperson. We are over time by 15 minutes, so we can have only 5 minutes break, coffee break now. Rush to get your coffee. We continue in 5 minutes from now. And I'm sorry for stopping. I apologize to Julian and Daniel for stopping this discussion. I would have liked to know the answer, but
we can discuss later. Yeah.
Okay, so as I said, the session will reconvene in 5 minutes from now.